Alright, hello there ROS developers. Finally we have been able to start the stream. Hopefully everything is fine, you can hear me fine, you can see me fine. I will make sure in a moment about this, but I don't want to lose any time, so let's start. So hello there ROS developers. First of all, I want to make sure that everything is fine because I have been having some trouble here in order to start the stream with the setup, configuring OBS. So let me know please if everything is fine. You can see me properly, you can hear me properly also, which is super important so that I can continue without worry. Can't hear. Audio is a bit quiet. Voice is really low. Okay, so it's low or you cannot hear. Okay, let me try to fine tune this. Is it better now? Maybe? A bit louder? Now it's better? Low, low, very low, very low. It's low. I think I have yes. Okay, I think yeah. So I have touched here the configuration in order to increase a little bit the volume. Good. Keep talking, please. Okay, yeah. So hello, my name is Alberto. Hello. Yeah, it's better. Yeah, it is better. Okay, so let's keep it like this. In case you hear me low, just try to increase a little bit the volume on your end so that you can hear me better. Okay, because here I have already increased the filter so that in theory you should be able to hear me better. Yeah, I can see better, but still low. Here. Try to put this better here. Okay. Great in my end. Okay, says Whale Mesele. Okay, excellent. So let's keep going. So audio is good and video is good also, as I can see. So welcome everybody, guys. We are in live class number 98. So only two remaining for reaching the 100th live class. So we are almost there. Then today we are going to be talking again about some kinematics concepts, specifically about kinematics of a holonomic robot. Yes. So some live classes back, I don't remember exactly which number it was, we were discussing about the kinematics of a differential drive type of robot, and in this case we are going to be checking a little bit and doing some exercises, some practical examples about kinematics of a holonomic robot. Yeah. Then yeah, welcome everybody. So since we are already have started late, let's not lose any more time with the introductions and let's go for it. So as always, I'm going to take a quick drink here on my ROS Developers mug. Cheers, and let's go to work. So here I'm in the ROS Development Studio and I'm going to share real quick today's project with all of you guys. So let me put it here. All right, excellent. So here I have shared with you guys the project link. So as always, remember, once you click on the link or you paste it here to your browser URL, whatever you prefer, then you are going to receive this project, this one in this case, which is the one for the live class number 98 in your workspace. Yes, you will need to log in, of course, in the ROS Development Studio if you already have an account. If you don't have an account, just create it. It will take you less than 1 minute and it's completely free. So just create the account and then you are going to have this project into your workspace at the ROS Development Studio. Yep. Then once you have your project, all you have to do is to just click here on the open button and open project, and this is going to start loading all the environment, this project environment, so that we can start working. Yes. So meanwhile this project loads, it can take, depending on your internet connection also, it can take up to 2 minutes, something like this. So meanwhile, I'm going to keep talking here a little bit. So as I've said before, we are going to be talking about mobile robot kinematics in today's class, and specifically we are going to be talking about kinematics of holonomic robots. Yes, then this project is part, let's say, of a course that we have added recently. Let me show you here. I'm going to click here in the ROS courses, which is going to take me here to the Academy. And here you're going to be able to see the new course that we have added, where all these topics are discussed, which is the mobile kinematics. Let me see if I can find it. I'll better say search it. We are starting to have lots of courses, honestly. Okay, here I have it. Yes, basic kinematics of mobile robots. Yes, so in this course that we added maybe 1 month ago, something like this, so it's quite new. You will have all these concepts explained more in depth with many practical exercises, etc. Yes, so we have all the different units starting from the basic concepts and building up from there on kinematics of non-holonomic robots, kinematics of holonomic robots, also some kinematic control, open loop control and feedback control. Yeah. So if you are interested in today's topic, in today's class, and if you like it, I really encourage you to have a look at this course, where you are going to be able to learn much more about kinematics of mobile robots. Yeah. Also, just let me remember you that this past week also we added 2 new courses, which were the machine learning for robotics, also super interesting course, where you are going to be able to learn machine learning concepts applicable to robotics and understand fundamental principles of artificial intelligence, and also a course on OpenCV. Yes, where here we have it, where you are going to be able to learn many things of OpenCV that you are going to be able to apply to your robots in order to add perception to these robots, a perception of the environment. Yeah, many topics like face detection, people tracking, object recognition, etc., etc. Yes, so 2 super interesting courses. And yeah, so let me come back here to my project, which has already loaded in order to start. Then here I have my notebook. I'm going to maximize it a little bit here. So here I have my notebook loaded for the live class number 98. Yes. So have you been able, guys, let me know now, have you been able to load the project properly? Yes. Yeah, guys, I know, I can see here some people that is saying that the audio is a bit low. Some people say that using earphones, headset, the audio is okay. I don't know, as I've said, everything that we had pre-configured has been lost for today's live class, so I had to in a hurry try to configure everything from zero again. All these things happen always before a live session, so I had to configure everything from zero. So maybe the audio it's not perfect, but I prefer to do the live class so that we don't lose more time configuring things. Then I prefer to do the live class so that we can keep advancing, and we will try to have everything 100% configured for future live classes. All right. Yes, still loading. Yes, project loaded. Yes, still loading. Open now. Okay, so I see that most of the people has already his project opened. Excellent. If not, don't worry, it will load in just some seconds. So let's go for it. Then about this project. Today we are going to be working with MPO 500 robot from Neobotix, which is this one we have here. Yes, then in order to start the simulation, as always, what we are going to do is to come here to the simulations button and click on the choose launch file. Yes, then here we have the package name and launch file name that we need to select. The package name is Neobotix description and the launch file name is MPO 500 controller.launch. So once I click here, I'm going to look for the Neo description. Here I have it, and within this package, I need to find the MPO 500 controller, which I have here, MPO 500 controller.launch file. Yes? So I'm going to select this launch file and click on the launch button. Then this is going to automatically open here a Gazebo window, as you can see, where the simulation, the Gazebo simulation for the MPO robot is going to be loaded. Yeah, here it's being loaded. It might take some seconds to fully load. But not more than 1 minute, let's say at maximum. Here I have mine already being loaded. There we go. Excellent. So here I have my Gazebo simulation. As you can see, it's an empty world with the Neobotix MPO 500 robot loaded here, which is the robot that we are going to be using for today's live class in order to demonstrate some kinematics concepts for holonomic robots. Of course, this is a holonomic robot in this case. Yeah. So let me know also if you have been able to properly load the simulation, because right now next step is to start with the class. Yes, so what I want you all guys to have is this same setup as I have, with the notebook here opened and the Gazebo simulation here also opened, in order to be able to start working with the class. Yes, so let me know guys if you are set up also, so that we can all start with the live class. Simulation loaded. Simulation loaded. Excellent, then let's go. If it is still loading, don't worry, it will load in the following seconds. So, first of all, as I've said, and you can see here from the title, we are going to be talking and discussing about kinematics for holonomic robots. So some previous concepts that we need to set up. First of all, what is kinematics? Well, in this case we know kinematics as the study of the motion of an object, in this case a robot, without considering its causes. Yes? So we are going to be studying the motion, the movement of the robot without caring, without taking into consideration what is causing that motion. We are going to study the motion, the movement itself. Yes? Then what do we mean by motion? Well, by motion we refer to the movement of the robot. Yes? The speed, the velocities, accelerations, etc. Yes? And what do we mean by causes? Well, by causes we refer to what provokes this motion. For instance, a force or a torque. Yes? Then what we are going to be studying are these, the motion, speed, velocities, etc., without considering the forces that are behind this motion. Yes? Then in this live class, we are going to be focusing a little bit on the kinematic model of a holonomic robot. Yes? So we know what is kinematics, but what is a kinematic model? Well, what is a model first? Then, what is a model? Well, in mathematics, we understand a model as a simplified and mathematical representation of a real physical system. Yes? In this case, it's a simulated system. Yes? But it's a simulated physical system. Then, a model is a simplified mathematical representation of a physical system. Yes? So, first of all, a model is a simplification. It's a simplification because we need to assume certain things. Yes? We need to simplify the system. Why? Well, because it's impossible to capture all the complexity of a real physical system. Yes? There are too many things to take into consideration. Then this is not possible. So we need to assume some things. Yes? This is why we say that a model is a simplification. And we also say that it's a mathematical representation. So what does this mean? Well, it means that a model basically is a set of mathematical equations. Yes? Then these mathematical equations are meant to describe the behavior of the physical system in this case. Yes? Then what is a kinematic model? Well, a kinematic model then of a mobile robot in this case is a set of equations that will describe the behavior in terms of kinematics, in terms of motion of this mobile robot. Yes? So, we are going to be talking about this kinematic model of a holonomic robot. Then, what is a holonomic robot? Well, basically, in general, we can differentiate into two different types of robots, non-holonomic robots and holonomic robots. Yes? In this case, a holonomic robot is a robot that doesn't have any restriction, so it can move in any direction, in this case, except in the z-axis. Yes? So a holonomic robot, in this case, can move along the y-axis, can move along the x-axis, and can also rotate along the z-axis. Yes? The main difference in this case, so that everybody understands, the main difference with a differential drive robot, for instance, is that a differential drive robot cannot move in the y-axis. Yes? Cannot do this movement. So a differential drive robot can also move in the x-axis, can also rotate in the z-axis, but cannot move in the y-axis. Yes? So in this case, what we are going to discuss is the kinematic model of a holonomic robot, which in this case, this MPO can move, can do this lateral movement in the y-axis. Yes? Then, what happened here? All right, then, in this case, the kinematic model that we are going to create, that we are going to describe for this robot, is going to tell us how wheel speeds map to robot velocities. Yes? So, in this case, we can see that we have a four-wheeled robot. Yes? So this robot has four wheels, two here and two here. Yes? Then, with our kinematic model, what we want to achieve is to be able to transform velocities of these wheels into velocities of the robot. Yes? This is the purpose that we want to achieve with this kinematic model. Yes? Then, let me see real quick here. How to load? Gloria says, I'm still loading, but I can rewind the video to catch up. Great, Gloria. That's the attitude. Okay, I can see that some people is making questions, but you guys are answering those questions by yourself and providing support, which is excellent. So I'm happy to see that you are also collaborative and so helpful with everybody here in the stream, in the chat. Excellent. Then all right, so then we are going to assume that this robot, that our robot rolls on a hard, flat, horizontal ground without skidding. Yes? So this is a flat, horizontal ground without skidding, and we have a single rigid body chassis, like this one. Yeah, it's not articulated. All right? And our chassis has the following configuration, which represents the chassis frame relative to a fixed space frame in the horizontal plane. Yes? Then we are going to represent our chassis by 3 coordinates, which are alpha, x, and y. Yes? So this q vector, which has alpha, x, and y, is going to represent the configuration, the position, in this case, of our robot. Yes? So the configuration of our robot is going to be defined by its position in the x, y axis and the orientation, the heading of the chassis. Yes? And the velocity is going to be represented by the time derivative of these coordinates, as you can see here. Yes? So by deriving in time this orientation x and y coordinates, we are going to get the velocities. Yes? And also we are going to define the chassis planar twist by the following vector here. Yes? Angular velocity in the z-axis, linear velocity in the x-axis, and linear velocity in the y-axis. Yes? This is going to define the twist of our chassis. Yes? So, all right. Then all this we can express it with the following matrices. Yes? So the velocity of our chassis is going to be defined by its angular velocity in the z-axis, linear velocity in the x-axis, linear velocity in the y-axis. Here we have the first matrix of 3 by 1, yes, which equals to this 3 by 3 matrix multiplied by the time derivative of phi, orientation of the chassis, x position of the chassis, and y position of the chassis. Yes? So then we have this system of matrices which is going to define the twist velocity of our chassis. Yes? Not of the wheels, not of each of the wheels, but of the chassis. Yes? Our chassis twist velocity is going to be defined by this system of matrices. Yes? Okay, then, yeah, wheeled robots may be classified in 2 major categories, which are holonomic and non-holonomic robots. Yes, I have already done a little introduction on this subject. Then omnidirection wheeled mobile robots typically employ either omni-wheel or mechanism wheels. Yeah? By clicking here on these links, you can get more information of what these omni-wheels look like and how they work. The same for mechanism wheels. In our case, our robot is employing this type of wheel, yes, these mechanism wheels, yes, which are used also by other holonomic robots, like for instance, it could be the Summit XL, it comes now to my mind, yes, which also has these mechanism wheels. Yes, so you can get to these links in order to get more information about this. I'm not going to go too deep right now. Here we can see as well an example and how these wheels work in a more mechanic way, which I don't want to enter too much because I want to focus more on the robotic part and on the ROS analysis and practicing with ROS, all this theory that I'm introducing here. Then this is I do want to remark it. So the most important question in kinematic modeling is, given a desired chassis velocity, yes, at what speeds must the wheels be driven? Yes? So for instance, if I say, hey, I want to move my robot forward at a velocity of, let's say, 0.5 meters per second. Yes? I want to move my robot in this direction at this speed. Then in order to reach this motion, what are each wheel velocity that I have to apply to the robot? Yes, so in order to move this robot in a specific direction at a specific speed, what are the velocities that I have to apply to each one of the 4 wheels? Yes? This is the most important question in kinematic model, and this is what we are going to try to solve in today's live class, yes, and to model. Then, the kinematic model of our robot, of a 4 mecanum wheel robot, like this one, like the one we have here, it's this one, yes? We have the U matrix here, which is a 4 by 1 matrix, which defines the speed of each of the wheels. Yeah, we have U sub 1, U sub 2, U sub 3, and U sub 4. Yes, these U's represent the speed of each one of the 4 wheels. Yes, then this can be here equal to 1 divided by r being the radius of the wheels. Yeah, U is the vector of wheel driving speeds, as I've said, so the speed of each one of the 4 wheels. Then r, this r we have here, is the radius of the wheels, multiplied by this 3 by 4 matrix we have here, yes, where L and W are the dimensions of the chassis. Yes, we can see this here in this scheme here. Yes, so this is the scheme, let's say, of this robot, where we have the 4 wheels. Then we have L, which is going to be the distance from the center of one of the wheels to the center of the chassis, and W is going to be the distance from the wheel here to the center of the chassis. Yes? So L is going to be the distance here from the center point of the chassis to the center here of the wheel, this distance, and W is going to be the distance, again, here from the wheel to the center of the chassis, in the y-axis in this case. Yes? Then finally, this is multiplied by the twist of the chassis, yes, which is the angular velocity in the z-axis, linear velocity in the x-axis, and linear velocity in the y-axis. Yes, we also have here into consideration the delta here, which is the angle at which free sliding occurs. Then, for instance, for this robot, in order to move in the x-axis, so let's define here, what happened here? All right. So here we can see z-axis, x-axis, which is the red axis, and y-axis, which in this case is the green axis. So, in order to move the robot in the x-axis, in this case in a positive value in the x-axis, which would be this motion, yes, all the wheels will drive forward at the same speed. Yes, so if I apply a velocity of 0.5 meters per second, a positive velocity of 0.5 meters per second to all the wheels, to the 4 wheels, the robot is going to move forward in the x-axis at 0.5 meters per second. Yeah? Then to move in the direction, in the y-axis, in the positive y-axis, to do this, oops, sorry, I moved it here in the z-axis. I don't know what I am touching here. Let me refresh this. Real quick, there we go. Alright, then, let me set again show here again the axis. Then in order to move in the y-axis, which is this movement, positive y-axis, then wheels 1 and 3, which are this one and this one, will drive backward, and wheels 2 and 4, this one and this one, will drive forward at the same speed, of course. And finally, in order to rotate in the counterclockwise direction, wheels 1 and 4 will drive backward, and wheels 2 and 3, these ones, will drive forward at the same speed. Yes? Does it make sense? Alright, let's test this right now here with doing some examples. Yes? Then, okay, so here what we are going to do is to start doing some practice. Then for this, what we are going to do is to execute this cell we have here. Yes? Run cell. So, basically, as you can see here, we are going to import ROSPy, some modules like math, numpy. Also, we are going to import the float32 multi-array from a standard messages package. Then we are going to initiate a node here, and we are going to create a publisher which is going to publish into this topic, wheel speed. It's going to publish messages of the float32 multi-array type. Yeah? Then, this wheel speed, basically what we are going to be able to publish is to publish the velocity at which we want to move each one of the wheels. Yes, we will see this right now. Then, yes, so as here we have all the possible motions, here, forward, backward, left translation, right translation, counterclockwise rotation, and clockwise rotation. Yes, here we have the definition and how we should apply speeds in each one of the wheels in order to achieve these basic motions. Yes, for instance, in order to move forward, all wheels drive forward at the same speed, with positive values, of course. In order to move backwards, all wheels drive forward at the same speed with negative values. Then left translation, for instance, wheels 1 and 3 drive backward, and wheels 2 and 4 drive forward at the same speed, etc., etc. Yes, here you can have a look at all the basic motions. Then what we are going to do here is to do some tests. Yes, so we are going to send values, velocity values for each one of the wheels. Yes, as we can see here, we define the forward motion as a list, an array of 4 values, which are all positive with the same speed. In this case, this is 1 meter per second. Yes? So in this case, we are going to send a velocity of 1 meter per second to all the wheels of the robot. Then, in theory, yes, in theory, if this is true, if what we have just told is true, the robot should move forward, like we can see here in this small GIF. Yes? Then, once we define these velocities, we are going to put them here into a float32 multi-array type of message, and then we are going to publish this message using the publisher here that we have just defined. That is going to publish this message into the wheel speed topic. Yes? Which is the topic that this robot is listening to in order to provide speeds to the wheels of the robot. Yes? So, with this code here, if we execute it, what it should happen is the following. So, the robot should start moving forward, yes, should start moving forward at a speed of 1 meter per second, and after 5 seconds, because here we have this sleep for 5 seconds. So after 5 seconds, the robot should stop, because I am going to publish, I am going to send speeds of 0 meters per second. So the robot is going to stop. Yes? Then what do you say? Let's test this. So let's test what happens here. Then if I click here on the run button in order to run this cell, I'm getting here a strange... okay, this is because I have not executed this cell. Yeah, so first I need to run this cell. Yeah, guys, I forgot to execute this cell. So first of all, I need to execute this cell in order to import everything I need and initialize the ROS node and the publisher. So let me run this cell, there we go. And now once I run this cell, I'm going to be able to execute as well this cell. So let me click here on the run button. And as you can see, the robot starts moving forward for 5 seconds and then it stops. Yes? Does it make sense? So for instance, now I can give negative values to all the velocities, and what is this going to do? Well, what this is going to do is to move the robot backwards, right? In theory, what it should happen is exactly the opposite movement. So the robot should start moving backwards for 5 seconds, and after 5 seconds it should stop, right? So let's try it. Let's run this cell with these values, and we can see the robot starts moving backwards, and after 5 seconds it stops. Yeah? Great. So we have verified at least the forward and backward motions. So by providing the same velocity to all the wheels, we can achieve the forward and backward movement in this holonomic robot, in this 4-wheeled holonomic robot. Yeah? Then what we are going to do here is to do a quick practice, a quick practical exercise. So let me do it here real quick. So I'm going to open a shell for this because I'm going to be creating a new package. Then here inside the CAD-King workspace SRC, I'm going to create a new package, as we can see here, CAD-King create package called Motion MPO 500. I'm going to give ROS-Py dependencies because I'm going to be creating here Python scripts. So I'm going to create this package. There we go. So I created this package, and right now I'm going to switch to the IDE to start working from the IDE so that I can visualize everything better. So let me just put this into the background and make the IDE bigger. So now what it is asking me to do is to create this basic motion Py script. Yes? Then this basic motion Py script basically what does is to test all the basic motions. So I'm going to create here inside my package, which I have here in the CAD-King workspace, I'm going to create here this basic motion.py file. Oop, I'm not writing. Basic motion.py. And I'm going to paste this code, which I have not copied for some reason. So let me come here and copy all this code. Control C, Control V. Yes, so let's quickly review here a little bit what is going on here. So as you can see, basically here what we are doing is to test all the movements. Yes, so here we are importing ROS-Py, we are importing the float32 multi-arrayed message, then we are initiating a ROS node, we are creating a publisher for the wheel speed topic, and then here we are going to test all the motion. So first of all, we have the backward motion, where all the wheel speeds are set to the same negative value. In this case here we have the left motion, yes, where wheels 1 and 3 are going to have negative values, and wheels 2 and 4 are going to have positive values. Yes, the right movement, right translation. Yes, this is the movement. These left and right movements are the movements in the y-axis. Yes, this translational movement. Yes, this one in the y-axis. Yes. then they are basically the opposite. So for the left translation, we have negative values in wheels 1 and 3, and for the right translation, we have negative values in wheel 2 and 4. Yes? We also have the counterclockwise rotation and clockwise rotation, and finally the stop movement. Yes? So this basically is going to test all the basic motions, and finally it's going to stop the robot. Yes? It's going to test all the basic motions for 1 second, and at the end it's going to stop the robot. Yes? So let's test this. Let's test this script and see if it works as expected. So what I'm going to do here, well, first of all, what I'm going to do is to make sure that my script has execution permissions. There we go. It doesn't have, so I'm going to provide them. Cmod +x basic motion .py. There you go. So now I'm able to ROS run motion MPO 500 and my script, which is basic motion. So let's execute it and let's see what happens here with our robot. If it does all the motions. Okay, backwards, left translation, right translation, clockwise, counterclockwise, and it stops. Okay, so this has been super fast. Hard to visualize. You can, if you want to make the movements last longer, you can increase here the time of the sleeps, right? For instance, I'm going to do it here real quick. 3. I'm going to set it to 3 seconds instead of 1, which is too quick. Yes. So now if I run again my program, I'm going to be able to better see the motions. So first we have the backward motion, here we have it. Now we have the left translation, right translation in the y-axis. Then it's going to start rotating counterclockwise. Now clockwise, and finally it's going to stop. There we go. All right, so we have tested all the basic motions, and we have confirmed that what we have deduced here, in order to reach the motions, it's true, yes? So now we know how to apply velocities to all the 4 wheels in order to achieve a certain chassis motion, yes? If I want to move my chassis forward, I know that I need to apply the same velocity, positive velocity, to all the 4 wheels. If I want to do a translation in the y-axis, I know that I have to apply positive velocities to 2 of the wheels and negative velocities to the other 2 wheels, yes? So I know this now. All right? Then, let's keep moving with the last exercise. Okay, so right now, what we have seen, let me get a quick drink because my throat is getting dry. All right, so what we have seen now is we have tested, we have checked what wheels we need to move and what velocities we need to send to each of the wheels in order to reach a certain chassis velocity, yes? But in ROS, as you might already know, yes, and in general, in robotics, it's better, or for us, for humans, it's more logical to think in terms of twists, yes, in terms of robot velocities, yes. So if I ask any of you, hey, what should I do in order to move the robot from this position to a position here, yes? Then probably you would answer me, okay, so you need to move the robot forward for 5 seconds, then turn to the left for 2 seconds, and then keep moving forward for 3 seconds until you reach the point, right? This is probably, you are going to probably tell me something like this. You are not going to tell me, okay, so you need to apply this velocity to wheel 1 and wheel 2, and this velocity to wheel 3, yes, this is not normal to think about in this way, in terms of wheel velocities. But it's more natural to think in terms of twists, in this case, of chassis velocity. Yes? Move forward, turn to the left, turn to the right, yes? So this basically in ROS is treated with twist messages, yes? So here, probably most of you, if you are familiar with ROS, know what a twist message is, yes? ROS message show twist, here you have it, yes? So a twist is a type of ROS message which is meant to send velocity commands to a robot, yes? It's composed of two vectors. Yes, the linear vector, which contains the linear velocities in the x, y, and z axis, and the angular, which contains the angular velocities in the x, y, and z axis. Yes, in this case, as we have seen here in the matrix of our model, our robot, yes, has angular velocities in the z axis, which is this W, has linear velocities in the x axis, and it has linear velocities in the y-axis, yes? So from this twist message that we can see here, we have angular velocities in the z-axis, so this variable here, and we have linear velocities in the x and y-axis, these two variables here, yes? And this message is the one used in order to move, to send velocity commands to mobile robots in ROS, yes? So, in order to move my robot, yes, remember that our goal, yes, the goal of our kinematic model that we have defined here is this one. So, given a desired chassis velocity or twist, at what speeds must the wheels be driven? Yes? So, given a specific twist message, what are the speeds at which the wheels need to move in order to reach this twist velocity or this chassis movement? Yes? Then, in order to do this mapping, in order to map this twist message into wheel velocities, what do we need to do? Well, we need to use our kinematic model, which is defined here. Yes? As you can see, this kinematic model is mapping wheel velocities, which we have here. It's mapping wheel velocities, which are defined in this matrix with the u values. It's mapping them to twist velocities that we have here. Yes? So, in order to do this mapping, to convert an incoming twist message into actual wheel velocities, we need to use this kinematic model. Yes? So, in this last practical part, in this last exercise, what we are going to do is exactly this. So, we are going to create a function which is going to be called twist to wheels, because it's going to convert twist velocities to wheels velocities. Yes? Then for this, we are going to create here a new Python script named make_turn.py. So let me create this file here, make_turn.py. There we go. Yes? Then, in this case, this would be great if you try to do it by yourself. Yes? However, here this is a live class and we don't have the time, so in this case I'm going to provide to you already the code, and we are going to review it. Only review it and test it, of course, afterwards, yeah? So here at the bottom you are going to find the complete code for this make_turn.py. Yes? Then basically what we are going to do here is to try to reproduce this motion, yes, this turn, yes. Then in order to reach this turn, what we do is to apply a linear velocity in the x-axis and at the same time an angular velocity in the z-axis, yes? So combining the angular velocity in the z-axis and the linear velocity in the x-axis, what I'm going to achieve is this type of motion, yes? This turning motion, yes? Then for this, what we are going to do is to use this snippet of code, yes? So as you can see here, we are going to call this twist. Okay, let me go straight to the code in order to review the full code. Yes. So let me come first here to the main section of the code here. Yes, to this section here. So here what we are doing is we are importing the models we need as well as the flow32 multi-array type of message. We initiate a ROS node and we create a publisher for the wheel speed topic, as we have been doing in the previous practices, yes? Then here what we do is to call this twist to wheels function. And we are passing 3 arguments. Yes, we are passing 3 arguments to this function. The angular velocity in the z-axis, which is in this case 1.5 radians per second. We are passing the linear velocity in the x-axis, which is 1 meter per second in this case, and for the linear velocity in the y-axis, it's going to be 0. Yes? So basically we are providing a linear velocity and an angular velocity, a linear velocity in the x-axis and an angular velocity in the z-axis. Yes? These 2 velocities are the velocities that are going to cause this motion that we can see here. Yes, this turning motion. Yes? Then the twist to wheels function is going to return me some values. Yes? It's going to return me the u values. Yes? So basically here I am providing these values that we have here in the last matrix. Yes? So I am providing these values, and the twist to wheels function is going to compute all these equations that I have here, and it's going to provide me, it's going to give me the u values. Yes? Does it make sense? So I'm inputting the twist values, which are these values, and I'm going to receive as an output of this function these values. We are going to see now what this function does inside. Yes? What else? Then finally what I'm going to do is to publish these u values as we have been doing in the previous examples. Yes? So as we have been doing here, for instance. Yes? So we are going to get these u values, then we are going to publish these values into the wheels speed topic. Yes? For 1 second in this case, let me increase this time so that we can see it better. 2 seconds. Yes? And then afterwards I'm going to stop the robot. So I'm going to set the velocities to 0 so that I stop the robot. Yeah? Then the most important part here is, of course, the twist to wheels function. So inside here what I am doing, as I have just said, is I am getting as input the twist values, which are these ones here, and I have to provide as output the u values, which are the wheels speed. Yes? So for this, what do I need? Well, I need to make these calculations that I have here in this matrix, yes, in this 4x3 matrix. So for this, first of all, I need some parameters of the robot. Yes? So I need to know the radius of the wheel, I need to know L and W. Yes? Then for this, in this case, we have obtained them here from this scheme that we have here of the robot, this datasheet of the MPO 500 robot with all the distances, all the chassis distances, etc. Yes? So from here we have obtained these values. Then these values we are setting them here. We have the L value, the R value, and the W value. Yes? So these values we obtain them by measuring in the robot. Yes? Well, basically all the robots are going to provide you already this data. Yes? In the specifications, in the datasheet of the robot, you're going to have these values. Yes, what are the radius of the wheels, what are the distance from the center of the wheel to the center of the robot, all these values are provided by you. Yes, in case that you design the robot by yourself, that you create a custom robot, whatever, then you are going to know as well these values because you are going to design it, right? Then, once I have these values, and I have the twist, let me come back here to the matrix. So once I know the R, L, and W values, and I have received as input the twist values, I can calculate, as we can see, the U values. Yes? Which is the purpose of this kinematic model of equaling here the U vector to this set of equations. Yes? Then, as we can see, once I have these values, all I have to do is to calculate the matrices. Yes? Which is exactly what I am doing here. Yeah? So, here what I am doing is to define this 4x3 matrix and divide it by the R. Oops, I have moved something here. Sorry, I have changed this and I cannot come back, so I'm going to copy again the code. Let me come here and copy everything again. There. All right, there we go. Yes, so as you can see here, what we are doing is to compute generate this matrix. Yes, this one here, it is exactly the same one, as you can see. Yes, we are filling this matrix with the L and W values. Where it is? Here it is. Yes, and dividing it by the radius of the wheels. Yes, so this is what we are doing here. Yes, once I have the L, R, and W values, I can do this. Yeah? Then, next what I am doing is to define here another matrix of 3 by 1, which is this one. Yes? This matrix, the twist matrix, it has a shape of 3 by 1, as we are doing here. Yes? And we assign the values to this matrix that we have received here as parameters of the function, WZ, Vx, and Vy. Yes? Then finally, what I am doing here is to multiply our H matrix that we have calculated here by our twist matrix. Yes? So we are multiplying the result of this 3 by 1 matrix by the result of this matrix divided by R. Yes, so we are multiplying all this, and then by doing this multiplication, what I'm going to do is to get the U matrix. Yes, the U values, so I'm going to get the speed of the wheels. Yes, here in the U variable, I'm going to store this, and I'm going to convert the matrix here to a list. Yes, I'm converting it to a list because I want to save it into a float 32 multi-array type of variable, which is basically a list. Yes? So basically, as you can see here, this is just a Python implementation of our kinematic model here. Yes? As you can see, we are using here, let me come here. So in order to do all these calculations and everything, we are using here the NumPy module. Yes? So you can come here, we have a link here in the project of the NumPy module, which is a Python module that is going to help you to do matrix operations. Yeah, you can multiply matrices, divide matrices, etc. Yes, so we are using this NumPy module in order to do all these calculations. Yes, you can have a look in case you are interested. But basically, what we are doing here is to put in Python code our kinematic model that we have defined here. Yes? Then with this, basically what we are going to achieve is to map twist velocities. Yes, we are going to map incoming twist velocities to wheel speeds. Yes? Then let's test this. So let's see. If we input these values, if we input a linear velocity in the x-axis and an angular velocity in the z-axis, we should output a motion like this one. Let's see if it works. Let's see if our function works and converts the twist velocities into wheel velocities. So let me come here to the shell, open another shell here, there we go. First of all, let me give execution permissions here to the make turn script, and now I'm going to test this. ROS run motion MPO 500 make turn. There we go. Let me visualize here the robot to see if it works, and let me execute my program, and as we can see, it's working. Yes, so it is working. We have achieved the motion. So now what you can do is to test different velocities. So for instance, what happens if I set the angular velocity to 0? I set the angular velocity to 0, the linear x velocity to 1, and the linear y velocity to 0. So I'm only applying a linear velocity in the x-axis. So if I do this, what would happen here? What is going to happen in the robot? Exactly. The robot is going to move forward because I am applying only a velocity in the y-axis. So now, instead of the y-axis, in the x-axis, sorry, we set the linear velocity in x to 0, and we set the linear velocity in the y-axis to 1. What is going to happen now? Well, what is going to happen is that the robot should move in the y-axis, in this direction, right? So let's test it. There we have it. So the robot is moving in the y-axis, yes? So, as you can see, basically what we have created a program that can map any incoming twist velocity, any incoming chassis velocity, to actual wheel speeds. Yes? So we have created here the kinematic model for our four mechanism wheel holonomic robot. Yes? Which was initially the purpose of this live class and of this project. Yeah? Alright, so we are done. We have finished it. We have finished it with the live class. So yeah, I hope you've liked this live class. You've learned something new. From my point of view, this is super interesting. As I've said, if you like this, please don't doubt to have a look at our basic kinematics of mobile robots course. Yes, which is going to cover this subject with more depth. Is going to cover many other subjects like kinematics of non-holonomic robots, differential drive robots, unicycle, car-like robots, etc. Yes, so you're going to find all this in the basic kinematics of mobile robots. Yes, so yeah, from my side, this is everything. Thank you very much, guys. I'm going to switch back to my camera. Let's see the comments here real quick. Very clear, thank you, says Mohan Krishnan. Thanks, dude. You're welcome, Hamdi. Thank you. Says Usman as well. You're welcome, Usman. Can you conduct a live class on face recognition as a continuation from the previous face detection live class? Hope you consider it. Yeah, that's a good point. Cor Honke is suggesting this face recognition live class. That's a good suggestion. So I'm going to really take it into account. Jack Silverman is saying, don't you have a quick 1 hour online class like this? Well, no, our courses are more extensive, Jack, so they cover more topics. They cannot be done in 1 hour. You can do it at your own pace, yes, so... But what we have are the live classes. So each week, each Tuesday at 6 p.m. CEST time, each Tuesday at this time, what we do is this 1 hour live class, what we are teaching different topics. Each week we are doing a different topic. Last week we did live class on machine learning. Previous week it was on OpenCV, face detection, I think it was. So yeah, just stay tuned because each week we are doing these 1 hour live classes. Nice class, thank you very much. That was great again, thank you very much, engineering. Nice, thanks a lot. Thank you, William Bobadilla, Natnet. Amma Mazen Ali is asking, what will be the surprise for the 100 live class? I don't know. And even if I knew, I couldn't tell you, Amma. Because if I tell you now what is going to be the surprise for the 100 live class, it's not going to be anymore a surprise, right? So, yeah, think about it. All right. All right, guys. So thank you very much, everybody, for attending this live class. I hope you enjoyed it. Sorry for the trouble we had at the beginning. We had some technical issues here with the computer where we do the live classes, but hopefully we have been able to solve it quickly, and we have been able to do the live class. So thank you very much for your patience, guys, and yeah, I will see you next week. So until then, take care and keep pushing your ROS learning. Bye bye.